I am here today with Dan Romik, Professor of Mathematics at UC Davis. He has published a number of works on number theory, combinatorics, probability, and metric geometry. It is the last of these fields that today's discussion centers upon, since in recent days a claimed solution to the moving sofa problem has been published by Baek to arXiv. This paper can be found in the description. The problem asks what is the largest 2D shape that can fit down a 2D hallway with a 90-degree bend. Dan has spent some time on this problem, with a webpage dedicated to the topic, a couple of published papers, and was featured in the Numberphile video explaining the problem, the link to which can be found in the description. All right, so let's begin. How did you get into the moving sofa problem?
Well, it was kind of random. The moving sofa problem is a problem that I had read about many years ago when I was still an undergraduate, I think, and never really thought very seriously about it up to that point. I mean, I sort of regarded it as a kind of curiosity, really. But around 2015, I was kind of messing around. I was using 3D printers to create various interesting math objects or math-related objects. And I had this idea that the moving sofa problem would be a fun thing you could visualize using 3D printers, because you could print the L-shaped corridor, and you could print a sofa shape and kind of slide it around and see that you're able to fit it around the corner. So that's how I got interested in it. I kind of remembered that, and I went and downloaded the paper that had been published about it by Joseph Gerver, where he derived the shape of his sofa that is now known as Gerver's sofa. And I created a 3D model of that. But in the process of doing that, I kind of became interested in the question itself and in the math that lay underneath. And then I just started working on it on my own for a while. And that's how I ended up writing a paper about it.
And so that led to a couple of papers, the problem that you wrote. What are those papers about? And between then and now, have there been any other major updates to the problem, or?
So I believe my paper, which I wrote in 2016, maybe was published, I don't know, like a year later or something. That paper, I think my more interesting discovery about the problem is that I was able to look back at what Gerver had done when he derived his shape. And I didn't really understand his techniques very well. I mean, I understood sort of the general idea of what he was doing, but I decided I'm just going to approach it in my own particular way and develop a way of looking at the problem. And that's how I came up with this idea of a system of differential equations that kind of encodes the sequence of motions that the sofa goes through as it rotates around the corner. And I was able to rederive Gerver's shape. That was like a minor result. I mean, I felt good about it, but I don't think it was that exciting. But also discover another shape that does the same thing for a different version of the problem called the ambidextrous moving sofa problem, where the shape is now required to be able to rotate both to the left and to the right. So that's sort of my main result. But in hindsight, the other things that I did in that paper, which was to kind of present a new point of view with the system of differential equations, I think that's what Baek is now using in his paper, where he's claiming to have completely solved that conjecture of Gerver's. So I guess, that might have been of some significance as well.
Yeah, can you say a little bit about that second paper as well?
Okay, so I mean, by that point, I was, already quite excited about this problem. I could see that there was a lot more going on there, sort of quite a very elegant and deep structure that I had not really than I had realized before. And I was thinking about what else can you do, and I noticed what seemed like a gap in the understanding of the problem, which is that we had a lower bound, meaning we had an explicit construction of a sofa, and no one could prove that it was the best one, but it was at least something you could aim for. And it had a certain area, which numerically is something like 2.2195. Now then, in these sorts of problems, you like to have a lower bound and an upper bound, and you like to push them as close to each other as possible. The upper bound, I noticed, was one that had been derived almost 50 years before and it was quite far from that value of 2.2195. It was 2.82. The exact value is 2 times square root of 2. And that kind of, I found that intriguing because, first of all, 2.82 is significantly more than 2.2195. So that suggests there is some room for improvement. And the other thing is that the proof of this upper bound was completely trivial. It was like a few lines of a calculation of a few lines. So I thought if you work harder, you should be able to say more, and you should be able to push that value closer to the known lower bound. And that's what I ended up doing with help from a very smart guy named Yoav Kalus, who ended up being my co-author on this paper. So we basically developed some computer software that had the ability to churn out rigorous new upper bounds for this problem that pushed the value closer to 2.2195.
Would you say there were any other major steps towards an optimal solution in the intermittent time between those sort of results and Dr. Baek's paper now?
No, unless you also include his own results. I mean, he had been thinking about this problem for several years now. He wrote his PhD thesis on it, and he has a paper which I believe is available in the archive with some partial results that he had been able to come up with prior to this complete solution that he is now announcing. But between what I did and what me and Yoav Kalus did, he was the next person to approach this after us.
So what is new about this particular paper beyond just the claim of optimality? Like what is the new technology or ideas and concepts that made this proof possible?
Okay, well, I should start by saying that I don't completely understand the details of this proof. I've looked at it. I mean, I've been in conversations with the Baek for some time, so I kind of have a decent high level understanding of what he's doing, but it's just high level. It's not really the details. But basically, with my paper with Yoav Kalus, we approached the problem as an optimization problem, but we kind of approached it in a numerical way. We're trying to just get the computer to use as much computing power as we have to produce numerical bounds. But it was clear that you could push this a little bit further, if you throw more computing power at the problem, or if you have better programming skills at the problem, you could bring the value down. But it was clear from the beginning that this was never going to get you to a complete solution. And even if you did it, it was in some sense pointless because it wasn't really adding anything conceptually. It didn't add any insight. It's just letting the computer calculate for longer. But what Baek did is he actually discovered a very intriguing set of ideas that were conceptual and new. And initially, he was able to use those ideas to prove some partial results, like I said. So in this paper of his from last year, I think, or maybe it's from earlier this year, he was able to prove a new upper bound for the area of a moving sofa of something like pi squared over 8 plus 1, which numerically is 2.23. That's much closer to 2.2195 than our bound. Our bound was 2.37. So that was already an indication that he has some really novel ideas that are worth paying attention to. And now he's pushed that all the way to the as far as you can hope to go, which is to prove that the 2.2195 is actually the correct value, that Gerver sofa is optimal. I mean, it's really a tremendous advance. Now, the main idea, as I understand it, is, which I really think is incredibly clever, is he came up with an idea that instead of optimizing the area of a sofa, which it sounds like area should be like a fairly simple thing to understand. But in the particular context of the sofa problem, area is a very elusive and difficult to understand quantity, because you're optimizing over a set of shapes or a space of shapes that is just very, very strange to describe, strangely behaving shapes. And understanding how and the area is sort of like a non-linear functional. It's a very badly behaving functional on this space. So what he did is he came up with a different functional that he replaced the area functional with a different functional that has the two essential properties. First of all, this functional is an upper bound for the area, so it's always at least slightly greater than the actual area of a sofa. Therefore, if you optimize over it, you'll be able to show an upper bound for the area of a moving sofa. But the second thing is that for Gerver's sofa, it is actually equal to the original area. So, and for sofas or for shapes that are near Gerver's sofa, that upper bound, that functional gets closer and closer to the true area. And the third property, I said two, but I guess there are three, is that this function is actually very well behaved. It's much, much nicer. He calls it a quadratic functional, and that means something technical, that in a certain system of coordinates that he uses to parameterize or to describe the sofa shapes that he's considering, that functional behaves essentially like a quadratic polynomial, like, y equals x squared. And everybody knows that quadratic polynomials are quite simple to understand. For example, they attain their minimum value at a unique point because they're strictly concave, or convex. They're strictly convex. I mean,
one or the other,
if you're looking at x squared or minus x squared. So he was able to exploit the fact that this function is well behaved and prove various things about it, and actually find a clean description for the place where that functional attains its maximum value, I guess, if we were thinking about area. Then and that place is exactly Gerver's sofa.
So what has your interaction with Baek been like? What is the extent of the relationship that you guys have had on this problem?
Well, he did everything by himself. I can't take any credit for anything that he's done, but he did discuss things with me. I was actually looking through my emails earlier today just to understand how long have I known that he was working on this, and I think the first email that he sent to me is like either 2019 or late 2019 or early 2020. So he's really been thinking about this for quite a while now, basically throughout his PhD studies, as I understand. Initially, we were just interacting over email because, I mean, he was kind of sending me some of his ideas and getting some feedback, and I was sending him some feedback. Eventually, we started meeting occasionally on Zoom. Again, it was just about him telling me about his ideas and me offering him some feedback. I mean, usually positive feedback. I mean, I certainly liked his ideas a lot, but also there was an issue of how he was going to write this and how turn it into a paper. So I gave him some advice about that. But and then he graduated with his PhD recently, and the next thing I heard is he just sent me an email saying, I'm writing a paper about the complete solution of the moving sofa problem, and he sent me a few drafts before it was complete. But now it's finished and it's publicly available. So I look at it with awe and wonder, just like everyone else, and trying to understand more of these ideas.
Are you at all surprised that this claim of a proof comes without any computer assistance, given your previous experiments with computer-based solutions? For example, had you been able to find an upper bound that exactly matched the Gerver sofa solution without just strictly using numerics, if you had been able to attain the upper bound that way and you already have a lower bound, that would have also constituted a proof of the optimality. So are you surprised that heavy numerics wasn't involved in this?
To some extent, yes. Well, maybe not heavy numerics, but first of all, it was clear that to solve this, you wouldn't be able to do it using just numerics. You would have to have some really new conceptual insights into the problem. That there would be an aspect or an element of your proof that has a really cool new idea, that's something that advances our understanding of the geometry here. Now, whether or not the proof would also use some computer calculations, based on his history, I would say it would be quite natural to think that there would be some computer calculations involved, because a lot of other problems with a similar flavor that were eventually cracked, did use some computer assistance. And also Baek himself, when he was working towards this proof, he kept saying that he was telling me how his proof works, and in his telling, there was actually a component using computer assistance, and he had developed a particular software tool that he called Sofa Designer. He mentions this in his preprint, so it's mentioned there as a footnote that he said, using Sofa Designer, I will be able to establish some key properties of a moving sofa, as a result of some computer-assisted calculations, and those key properties would serve him for the remainder of the proof, for the more human part. So that was my understanding of his plan. And then when he recently contacted me to tell me that he's almost finished writing this paper, and I asked him, to explain it again, like how he did it and what's going on, what types of techniques it uses. And at that point, he said there is no computer assistance. He managed to find a way to eliminate that completely, which I think is actually amazing. It's seriously cool. And I was very impressed, and I was surprised because my frame of mind at that point was that he will be using computer assistant.
So now, just to be clear, this is only a preprint, right? It hasn't been gone through the peer review process yet. Would you want to explain to the folks at home what the peer review process in mathematics looks like and how it differs from that of other academic disciplines, from what you've observed other people you might know in academia have gone through in peer review?
Yeah, for sure. So peer review, well, I mean, in general, in science and scholarly research of different types, when you write a paper and you want to publish it, then you submit it to a peer-reviewed journal, and the journal sends it out for peer review. That means they find people who are your colleagues, at different institutions around the world, but people who have the relevant expertise, they understand the area that you're working in, and they are well positioned to evaluate it. And particularly in mathematics, what we care about, or at least the first thing we care about, is that it has to be correct. Because if it's not correct, that's the end of it. No one's going to want to publish your work if it's not correct. If it's correct, it's still not completely clear that they will want to publish it, but at least that's the minimum. Now, when you're announcing the solution to a famous problem, the correctness becomes even more essential, because no self-respecting journal is going to want to publish the proof of a famous conjecture or a famous open problem without being certain, at some very, very high level of certainty that what you did is correct. So they will certainly send it out to probably at least 2 referees, because, one referee could potentially make a mistake and miss something about your proof, but 2 referees, maybe even 3 in some cases. So they want, and broadly speaking, they want the community of researchers to weigh in on this. Sometimes it can even, if it's sufficiently interesting, then probably experts will be looking at it regardless, sort of independently of the peer review process, and maybe discussing it online on blogs or various websites. So now, how does it differ from other disciplines? I would say, first of all, there is a much stricter sense of what it means for research to be correct. So if you're doing research in the natural sciences like physics or other sciences, you will do some experiments sometimes. There will be some data analysis, and you will want to have reasonable confidence that your methods are sound. But in the end, it's not completely black and white. Whereas in math, it really is completely black and white. That means the proof of the moving sofa problem is either correct or there's a mistake somewhere. Now, that's not to say that math research never gets published with small mistakes that somehow slip through the cracks. That does happen. Even with big results, it may happen, because it's just, from a practical point of view, if you have a paper of 100 pages or something, it's just hard. It's hard for human beings to go through such a large amount of material and spot every possible issue that may exist there. But at least with the proofs of big results that get published, you can be reasonably certain that they're correct. And if there are issues, there's also some issues which may be of a more fixable type than other issues. Like if there's something computational, maybe some calculation is a little bit off, but if the methods are sound, then typically a lot of the time those types of mistakes can be corrected.
Since this paper represents sort of a capstone on the whole moving sofa problem, would you expect the peer review process to be in any way changed? Would you expect more peer reviewers to be needed on such a claim?
I think it will come down to how easy it is, or how practical it is for this paper to be evaluated in a reasonable amount of time. I mean, the paper is long, and length by itself is not necessarily, like an insurmountable obstacle, because papers of this length get published all the time. But it would depend on the quality of the presentation of the proof, because a paper can be 100 pages long and could be a pleasure to read, where you sit down, you read it. It might take you a week or two to get through all the details, but you will be able to do this, and nothing, you won't feel that there's any particular challenge to verifying that the paper is correct. Whereas a different paper of the same length might end up being completely impossible to verify, because there are some significant issues with how it's presented, that the author just didn't do a very good job of putting in all the details that they should, of making sure that their definitions are very tight, that everything is clear, that all the claims are presented in an accurate way. Because mathematical writing is a form of writing. There's good writing, there's not so good writing. So if from what I've seen of this paper, I think it's quite well written. I think, and I hope, and I believe that it will turn out to be that it will be quite practical to verify in a reasonable amount of time. I mean, I don't know if it will take 1 month or 2 months or 6 months. It certainly will take a while, because it's a substantial work, and you have to really pay a lot of attention when you're reading something like that. But I think the community will be able to do that.
A couple more questions before we wrap up. If this is all correct and stuff like that, would this put Dr. Baek on a short list for a Fields Medal in the coming years, or is it not that significant of a problem?
I don't think it's for me to say.
Okay.
Nobody asked my opinion about short lists for a Field Medal or who should win it, but it's certainly a very nice achievement. I mean, the problems of this caliber are not solved every day, or maybe not even every year. So it's a really impressive achievement for sure.
Okay.
But there's a lot of very good work being done. There's not enough Fields Medal to give to all the people who are doing excellent work.
Mm-hmm. No, agreed about that. And final question, totally unrelated to the paper itself. Would you ever get any of these sofas for your living room?
If somebody gave them to me, yeah, I might. That would be a cool conversation piece, let's say, and maybe even comfortable to sit on. I know that some people have built furniture based on these shapes. Somebody sent me a photo at some point of a student, an undergraduate student somewhere sent me, was doing a woodworking project, or maybe a math project, and she was also liked doing woodworking. So she built one of these sofas just for fun. So yeah, why not?
That's cool. Okay, I think with that concludes the interview. Thank you for coming on, Dan. It's been a pleasure to have you.
Thanks, Art. My pleasure as well.
All right.